Hello and welcome to the video series on using high-level synthesis for implementing machine learning algorithms in hardware. This video series is intended to be an open-ended discussion, and so videos will be added in the future as additional topics become relevant. We will begin by covering the basics of high-level synthesis in order to understand why high-level synthesis is a good fit for implementing machine learning algorithms in hardware. First, we'll talk about the differences between training versus inferencing in machine learning, then some of the challenges when building machine learning or AI hardware, and then we'll look at the specifics of why Catapult high-level synthesis is a good fit for implementing machine learning hardware. Designing and implementing machine learning algorithms, both in software and hardware, can usually be broken down into two separate topics. Training takes a machine learning network designed by an algorithm engineer and computes weights to identify or classify something. Typically in training, we're talking about using very large data sets and large memory storage requirements, and the training is going to be done on a GPU or a TPU farm, and typically will be done in floating point. The process of training is not done in real time, and often training may take days, if not weeks, to complete. And lastly, training is usually done on some kind of machine learning framework, such as TensorFlow or Caffe. Inferencing is taking the results of the weights from the trained network and deploying them on some type of hardware, either general purpose or custom. It is possible that there may be millions of weights that need to be stored in memory, and this can present memory storage bandwidth challenges. The inference engine often has real-time or low-power requirements and may require some type of custom hardware implementation in order to meet those performance requirements. Lastly, inferencing can often be reduced to fixed point or integer hardware to dramatically reduce both the area and the power. The design of the inferencing engine is where Catapult is used. Next, we'll talk about some of the hardware design challenges we face when designing AI or ML hardware. The past several years has seen an explosion in the number of architectures for implementing inference engines in hardware. Each convolutional neural network layer has different properties. For the early layers, there's more data that needs to be processed and fewer weights, and for the later layers, there's less data and more weights. Machine learning architectures are rapidly evolving, and it's hard to know which one is optimal for each type of network. Furthermore, there's not enough time to build them all in RTL, so designers have to make a decision up front that may lead them down the wrong path. On-chip memory, memory bandwidth, power, performance, and area are all important, especially when targeting edge applications. Power must be taken into account when building an efficient memory architecture. Keeping the data on chip is key to minimizing power consumption, and this is extremely important when designing for ASIC. Research by NVIDIA and MIT in 2017 showed that the cost for retrieving data from system memory was over 30x more energy consumption compared to storing that data on chip in SRAM. Likewise, floating point is very costly for both area and power. Although floating point is needed and used in the training of networks, it is typically not needed in the network inference engine. And lastly, the precision of the inference engine implementation does not necessarily have to be a power of 2-bit width. Processor architectures are fixed at power of 2-bit widths such as 8, 16, and 32 bits, but as we will see, high-level synthesis lets us experiment with precision and further reduce area and power consumption. One of the keys to designing an efficient memory architecture is being able to leverage data reuse in order to improve memory bandwidth as well as lower power. Memory accesses are usually the performance bottleneck when building machine learning hardware. system memory is not going to be efficient for performance or for power. Most efficient implementations will need some type of local storage or on-chip caching in order to reduce memory traffic as well as reduce power. Furthermore, RTL verification can take a very long time when trying to verify machine learning algorithms implemented in hardware because of the massive amount of data and weights that need to be processed. Memory architectures often need to leverage not only data reuse, but also parallelism. It is possible that architectures may have or require multiple processing agents or processing elements, requiring both intra-block and inter-block parallelism. This possibly means having many local memories in order to split up the computation and bandwidth requirements, and understanding system-level performance is critical to meeting all of the requirements. And like the previous example, RTL verification can take a very long time, possibly taking days or weeks to verify an inference engine. So the question one might ask is, why is Catapult high-level synthesis a good fit for designing machine learning hardware? Catapult HLS is the best solution for rapidly going from an algorithm to an efficient hardware implementation. Designing using high-level synthesis enables late-stage functional changes without impacting design schedules. Algorithms can easily be modified and regenerated into RTL, and switching technology nodes is easy, such as either going from 14 nanometer to 7 nanometer, or from ASIC to FPGA. Designers get to quickly evaluate power and performance in area of an algorithm built to hardware, and ultimately the entire design flow is reduced, going from a year down to a few months, being able to add features in days and not weeks, and also producing 5x less code than RTL. Catapult synthesizes C++ or System C to synthesizable RTL. The advantage here is that machine learning inference engine hardware can be very complicated, and it's often very easy to get hand-coded RTL wrong, where the hand-coded RTL implementation does not match the original specification. Catapult's RTL output is correct by construction, and by this what we mean is that the Catapult technology is very mature technology, and so Catapult is able to reliably synthesize the C implementation into an equivalent RTL representation. So if designers do a good job of testing their C code to prove the functionality, the RTL will match that functionality. High-level synthesis gives designers the ability to quickly simulate the real hardware behavior in C++ or System C. Machine learning inference engines are computationally complex, often requiring tens, if not hundreds of millions of computations to process a single image or frame of video. Designing using high-level synthesis and bit-accurate data types provides the ability to perform rapid simulation of the true hardware behavior, where the simulation can be anywhere from 30x to 1000x faster than an equivalent RTL simulation. This means being able to simulate in minutes or hours versus hours, days, or weeks. Designing using bit-accurate data types allows designers to model any precision in C++ or System C and directly measure and observe the effects of quantization of an algorithm. Furthermore, precision can be arbitrary, so we're not limited to power of 2 bit widths. And lastly, because we're designing in C++, we have the ability to plug back into a machine learning framework such as TensorFlow using its C API in order to verify the quantization of the algorithm. One of the key advantages of the high-level synthesis that is driving adoption is the ability to automatically add data flow control to the design interfaces. Machine learning hardware needs to access system memory, local memory, as well as needs the ability to communicate between processes. Catapult can automatically add protocols using user constraints. These protocols can be complex, such as AXI master for slaves, AXI for streams, or simple point-to-point protocols using a data-ready valid signaling mechanism. For Untimed C, the source does not specify the protocol. The data synchronization and flow control is built into the interface. Data synchronization and flow control is built into the interface, allowing interfaces to start and stop the design as data becomes available. With MatchLib, the data synchronization and flow control is explicitly coded in the library description. Catapult high-level synthesis makes designing with memories easy. High-performance machine learning hardware will typically use lots of local on-chip memories in order to achieve performance requirements as well as reduce power consumption at the system level. Catapult can infer memories or registers from C++ arrays. The user has controls over the type of memory, such as single port or dual port. C++ arrays can be automatically mapped to ASIC or FPGA memories or registers, and a Catapult library describes the memory behavior, such as the address and data ports, the types of chip select and read enables and write enables. And because the memory behavior and control signals is accurately described in the Catapult library, memory instantiation and hookup is always done correctly. Arrays on the design interface will be inferred as a memory interface protocol consisting of address, data, and control signals, and internal arrays will be inferred as an instantiated memory wrapper where the address, data, and control signals are correctly hooked up for ASIC or an inferable memory for FPGA. Arrays on the design interface can also be synthesized as an AXI memory master or slave interface if a more complex protocol is desired. For System C, MatchLib memories are used on the design interface. Catapult HLS also lets users optimize the memory bandwidth using design constraints. High-performance machine learning hardware often requires complex parallel memory architectures. Designers can easily increase memory bandwidth by making a memory wider, allowing multiple data to be read or written in parallel. Designers also have control over memory partitioning. Block size and interleave constraints can be used to automatically split a large memory into multiple smaller memories. This allows the memory bandwidth to be matched to the algorithm bandwidth along with other high-level synthesis constraints. Catapult high-level synthesis makes machine learning performance goals achievable. Catapult performs all of the classic high-level synthesis optimizations typically focused on loop transformations such as loop unrolling, pipelining, and merging. Loop constraints allow designers to explore both parallelism and concurrency. The process of scheduling provides automatic time enclosure based on the target technology. A designer only needs to specify a clock frequency and a technology library, and the scheduler will pipeline the design to ensure that the worst-case timing path or clock period is not violated. And lastly, automatic resource and register sharing is always performed under the hood, so designers don't need to worry about managing variables in their code. Register lifetime analysis is performed automatically, and the tool will automatically reduce and share both registers and resources based on the design's performance constraints. Designing using high-level synthesis is not just taking C++ or System C, throwing it into the tool, and getting out RTL without